this is the shortest section of the aromatic compounds, and this is just phenols. We've done alcohols before, but phenols is very specifically a benzene with an alcohol group. So nomenclature, phenol, of course, for the benzene with the alcohol group. Cresols, if you remember, I kind of went over the nomenclature very slightly before, but anyhow, if you have a methyl group and an alcohol group on the same benzene ring, then it's called cresols, or you can just call it the normal name, which is 3-methylphenol. Okay, that will work. And then here are some of the ortho para diols. Okay, so the diols where you have two alcohol groups, so 1,2-benzene diol, 1,4-benzene diol, catechol, hydroquinone, the other one is called resorcinol. Okay, if you had it the meta position. So very specific names, for diols. Only people who are working with diols that much, they will remember it. If you don't, it's not a big deal. Just remember the IUPAC nomenclature, that's good enough. So where do you find phenols? You actually find them everywhere, okay, pretty much. So I've given you some examples over here. Eugenol is probably the most common one that you might have encountered, and that is in cloves. So clove oils or cloves, the wonderful aroma that you get from cloves is eugenol, so that's wonderful. And then vanillin, of course, is also another one that has an alcohol group, and I cannot imagine what we could do without vanilla, in our lives. So in any case, so all of these are naturally occurring phenols. Okay, this is not something you synthetically make, so they're all naturally occurring. So let's talk a little bit about the acidic properties of phenols, because just like alcohols, phenols will also be acidic. Now, alcohols in general are amphoteric, just like water, so they can be acidic or basic, depending on whether you're reacting them with an acid or a base. Phenols in general are a little bit more acidic, okay, in nature. So here is the pKa's for all of these. So acetic acid, which we know as an acid, is a low pKa. Phenol is about 10. Water is higher. Look at alcohol. Okay, so when we are comparing alcohols, then phenol is much more acidic than a normal alcohol. So what is it that is driving that acidic property of a phenol? Okay, so that we can show only by resonance structures. Yeah, everything comes down to resonance so many times. So here is a normal reaction that you can do, right? So this is the acidic proton, treat that with sodium hydroxide, and you end up getting an alkoxide, which in this case is phenoxide. Okay, so the phenoxide ion is coming from phenol. Now what happens to this phenoxide ion is resonance. Okay, because it is connected to the benzene ring, these electrons start delocalizing on the benzene ring. So I've given you all the resonance structures where you can see how the electrons are moving all over the benzene ring. So they are delocalized all over, okay, the benzene ring, which means it's a very stable sort of an intermediate. So if it's very stable, what happens? The proton does not want to come back. Okay, so if it doesn't want to come back, well, then it's going to stay in solution, which means that phenol is going to be acidic. Now that acidity of phenol, okay, or the generation of this phenoxide ion is actually quite interesting. So first of all, it makes it a good acid, okay. The second thing about the phenoxide ion is that because these electrons are involved in resonance over the benzene ring, it makes the benzene ring really a lot more nucleophilic. Okay, so we talked about alcohols being highly activating groups, and they are very activating groups, but now as a phenoxide, they're even more activating because they pushed even more electrons into the benzene ring. Okay, so let's look at that. So if you have substituents on phenols, that's also going to affect the acidity, okay, of the phenol. So here is a comparison of that, all right? So for example, and this is the phenol, here is a nitro group. So if you have nitro group, see what's happening here. The acidity is increasing, okay? And so the orthopara positions are also going to be, a factor here. So the meta position, not directly, in I should say aligned, okay, with the resonance structures. However, in the para position, then this proton is more acidic, okay, in nature. So it's a lot easier for this proton to leave, okay. And the nitro group in general is going to be, electron withdrawing group, and for that reason, any nitro group versus any phenol without a nitro group is going to be more acidic, okay, in general. The other part of that is then if you have an electron donating group. So if you have electron donating groups, those electron donating groups now make it harder for the hydrogen to leave. So in that case, the pKa will actually increase, which means that they do not they're not as strong of an acid as phenol would be. They're still good acids, okay, but they're not as strong as you would think, okay, for them. So I would need you to compare the acidity of phenols also, okay, when you have electron withdrawing groups and versus electron donating groups. I may not give you so much of an ortho para meta kind of things to compare, but I will give you different groups to compare, okay, in there. So now for the synthesis of phenols. Okay, in the synthesis of phenols, the one that you have learned so far has been this one, where you take bromobenzene and then you do an SN2 substitution on it to get phenol. Now this was an industrial synthesis, okay, for phenol, and it's very hard to do in the lab, okay. The other synthesis we're going to cover here also is an industrial synthesis, because the lab synthesis we're going to learn a little bit later when we do amines, okay? But right now we only have industrial synthesis of phenol, and phenol is actually a very good starting material for a lot of things, and that's why we have all of these syntheses for phenol. So this second synthesis of phenol is actually quite practical, because in this case you actually start with cumene, which is actually isopropyl benzene, and you treat that with oxygen. You end up getting a peroxide, which once cleaved with on acid hydrolysis, then you end up getting phenol and acetone. So you end up getting two products, okay, as a result of this synthesis. So industrially speaking, this is a very good synthesis, because you get two products that are highly useful products. So these are both syntheses that are industrial. Now the one, if I ask you to make me phenol, then this is the one that you can write for me, okay. This one is more industrial. I mean, you can make this, and acetone is just a solvent, but this is easier to remember, so use this one. So now for the reactions of phenols. Now I said to you phenol is a highly activating group. I mentioned that before, and then it does really unusual reactions. So we'll talk about the phenoxide also, okay, as to why that is an extremely good kind of a reactant, okay, for us. But first of all, very simple kind of reactions. Ethers, which we can make from alcohols, using Williamson synthesis. So you can do that also with phenols. So take a phenol, treat it with sodium hydroxide, get the phenoxide, then that can do SN2 reaction in order to get an ether. You can have any kind of alkyl halide here, no problem. You can get any ether. Okay, so synthesis of ethers, normal stuff. Okay, the unusual stuff is the Colby synthesis. The Colby synthesis is using the phenoxide. Okay, so here is the phenoxide again with the sodium hydroxide and phenol giving the phenoxide. Phenoxide makes this ring highly activated. So once it is super activated, it can just add on to carbon dioxide and give this kind of a carboxylate on the benzene ring. Protonating this will protonate both of these groups to give alcohol and carboxylic acid. This is salicylic acid. Salicylic acid is the precursor for aspirin. Aspirin was one of the first drugs to be synthesized, and sometimes a lot of people just know it by Bayer aspirin, because Bayer was the first company to synthesize aspirin. Otherwise, aspirin was actually obtained from trees before. So once the synthesis was accomplished and it was industrially made, no looking back. Okay, and we know how common aspirin is in everybody's life. So this is the way of making aspirin, and this is a very good way and a very practical way, okay, of making aspirin. Very efficient also. And then oxidation of phenol. So oxidation of phenol, I don't want to talk about the phenol per se. I want to talk about the diols. Okay, and specifically I want to talk about hydroquinone, okay, which is the one for the para positions, alcohols. So when you take this kind of a dihydroxybenzene and you oxidize it, you end up getting this kind of a quinone. And the only reason I'm talking about this oxidation is because this is really, really important in electron transport chains in human beings and in plants. Okay, so one of the common reactions that happens in all living beings is oxidation reduction. Okay, so oxidation is, removal of hydrogen, reduction is addition of hydrogen. So this is an oxidation reduction reaction going on. In our bodies, we also have enzymes that help us to do that. So when you breathe in oxygen, for example, you have oxidation going on, but then everything needs to be, recycled back. All the enzymes need to be recycled back. And so there's a whole sort of redox position, redox reactions going on in the body. And all of that happens because of this conjugated system that you end up getting from dihydroxybenzenes, specifically hydroquinone. This conjugation that you see here, this right here, follow my laser pointer. This is the electron transport chain. Okay, and so then if you have more conjugated systems in there, then they all cause the cascading effect of electrons. And that's how electrons move around in the body. Okay, now if you don't remember this, it's okay. You're going to do this in biochemistry when you learn all about oxidation reductions there. Okay, but this is kind of an interesting little thing about phenols. I think that's about it that I have. Yeah, that's it. So main thing from here, acidity of phenols and the ether synthesis. Okay, Colby, if you remember, that's great. And oxidation, don't worry about it too much. That's it.